Hello. In this video, we're going to be doing a few more convergence tests, comparison test, ratio test, and root test. And I really want to urge you here. I have this reminder. Please make sure you truly understand what you're doing. If you're trying to just memorize a bunch of stuff, this particular chapter is going to be so difficult. You really want to do it from a point of understanding. If you feel like you're just going through the motions, stop and get some help so that you understand things. So the main idea that's going to be going through this whole section is if we're looking at a series and we notice that it's reasonably similar to a series we already know that's convergent, then it converges. And similarly, if it's reasonably similar to a series that diverges, it diverges. Now, this is only helpful if we know some basic facts about familiar series and whether they converge or diverge. So what I want you to do is I want you to pause and just answer these four questions. What makes a geometric series geometric? When does a geometric series converge? And similarly with p-series, what is a p-series and when does a p-series converge? Pause and answer those questions to the best of your ability. If you cannot answer them, you really need to make sure that you are learning this. So a series is a geometric if we always multiply by the same ratio in getting from one term to the next. And division you can think of as multiplication by a fraction. So an example would be something like 2 plus 6 plus 18 plus 54. Here we're always multiplying by 3. And it converges if r is less than 1 in absolute value. A p-series is one of the form 1 over k to the same power over and over again. So for example, 1 over 1 to the third, plus 1 over 2 to the third, plus 1 over 3 to the third, etc. And a p-series converges when p is greater than 1. If p is greater than 1, then the denominators get big rather quickly. And so we have small fractions and we can add them together. We also want to make sure we're comfortable thinking about fractions and whether they're bigger or smaller. So pause and answer this question. What makes a fraction smaller and what makes a fraction bigger? What makes a fraction smaller is, and assuming we're dealing with positive numbers, let me just say that clearly. Throughout this section, assume everything we're talking about is a positive number. A fraction is smaller if we decrease the numerator or increase the denominator. If I have a fraction like 2 over 7, that's bigger than 1/7. It's also bigger than 2/9. And what makes a fraction bigger? We just flip this. We can make a fraction bigger by increasing the numerator or decrease the denominator. So series are just our attempt to add together an infinite list of things. And generally speaking, they're converging when the things we're adding are sufficiently small. We know they have to be approaching 0, and they have to be approaching 0 rather quickly. So let's finally get to a specific convergence test. And again, we're assuming everything is positive. Let's suppose we have two series, one consisting of A terms and one consisting of B terms, where for each index, or at least eventually each index. Sorry if this is not coming through great. I'm a little bit sick and I'm in an airport, but I'm trying to make use of my time. The A terms are always smaller than the B terms, right? So on a term-by-term basis, the A series is smaller than the B series. Well, if the bigger series converges, then so does a smaller series, right? If it's smaller than something finite, it's finite. And on the other hand, if the smaller one grows infinitely big, if the smaller one diverges, then the bigger one diverges. So we can only compare in one way, right? Smaller than finite tells us something, bigger than infinite tells us something, but not the other combinations. So take a moment and apply these tests to these three examples. Try to find out what could you compare them to that's a little bit easier to understand. So for this first one, we might note that 4 over 2 to the I plus 3 is smaller than 4 over 2 to the I. And this is a geometric series with R equals 1/2. Powers of 2 in the bottom mean we keep multiplying by 1/2, so this converges. So this first example is smaller than a convergent series, so it converges. This next example, 3 over root k minus 1, is bigger than 3 over root k. And if we have the series 3 over root k, that's 3 times this p series. But if we're just multiplying by a constant, we can pull that outside. So this is p equals 1/2. This is divergent. So this whole thing is infinite. I'm leaving out the infinities, it's kind of implied. When we're adding together a p series like this, it's infinite. This thing's even bigger, so this also diverges. And finally, this one, 1 over n squared plus 2, is smaller than 1 over n squared. This is a p series with p equals 2, so it converges. So this is smaller than a convergent series, and therefore it converges. So in each case, I compared it to a p series or a geometric series because I am familiar with those things. Now, what if we changed our last example from having a +2 in the bottom to a -2? Here, the comparison wouldn't quite work because unfortunately, now we have something that's bigger than our convergent p series. And being bigger than something convergent doesn't really tell us anything. Bigger than finite might be finite, or it might be infinite. But hopefully you have this intuition that when we go out to infinity, things like -2 aren't really going to matter. And we can address that with what's called the limit comparison test. So here's what we're going to do. We're going to basically say if two series behave similarly, it doesn't really matter which one's bigger or smaller, but if they are similar in their basic pattern, then either they both converge or both diverge. So what we'll do is we'll take the limit of the ratio of the terms, and we'll call that rho. So this is the Greek letter rho, it's lowercase. It's the Greek equivalent of the letter r. And the idea is it reminds us of r. This is sort of like a ratio, but not literally a ratio. We're not saying it's always the same ratio. It's like a ratio. It's the limit of the ratios. We'll see a few other examples where we call something that is like a ratio, but maybe not literally r, rho. So rho will be in the limit, what is the ratio between these two series, between the individual terms. And the idea is if rho is a positive number, so not 0 and not infinite, then either both series converge or both series diverge. Right? Suppose rho is equal to 7. That means in the long run, one series is exactly 7 times, well, not exactly. In the long run, one series is roughly 7 times as big as the other. Well, 7 times finite is finite, 7 times infinite is infinite. So as long as we can compare these with some fixed number that's not 0, then either they both converge or both diverge. So let's look at some quick examples. So here, this is the one we saw before. I might compare this thing to the version that does not have a +2 in it. And we know dividing by a fraction is the same as multiplying by its reciprocal. And the 4's cancel. And we know that this limit is 1. That +2 doesn't matter by asymptote rules, or you can do L'Hopital's rule. So we're comparing these two series, and we're saying in the limit, one is basically 1 times as big as the other, right? They're roughly the same size in the limit. And since we know this converges because it's a convergent p series, That means this top one converges. So this converges. Now let's look at this one. Again, we probably feel like the -1 and +1 don't really matter. So let's compare this to the version that doesn't have them. And here's actually what I'm going to do. I'm not even going to write the fraction. I am going to immediately multiply by the reciprocal. So we're comparing this to the version that doesn't have those extra constants. And if we want, we could switch the order here. This -1 doesn't matter. This fraction is 1 in the limit. This fraction is 1 in the limit. Oops, sorry, I put the +2 in the wrong place. So this is 1. It's another example where, in the long run, this is basically the same as the version that doesn't have the -1 in the top and the +1 in the bottom. But this is geometric with r equals 4/3, which diverges. So the series here is roughly the same size as something that diverges, and therefore it diverges. Now, generally speaking, we want you to be able to do these problems with a certain degree of intuition. By we, I mean me and the AP exam. I, on a quiz or test, might ask you for a brief verbal explanation of what you're doing, but you could just say, for example, this is like a convergent P series with P equals 2. You wouldn't have to show me all the limits. So get comfortable just feeling, relying on your feelings and intuitions. You do not have to write out every step if you know you could. When we get to the ratio test later in this section, that's the one that you have to know in some detail. That's the one that we'll practice presenting in a specific way. But generally speaking, these tend to show up in, say, multiple choice questions. So as long as you understand the relationships, you don't have to show things in great detail. All right. I need some water, so I'm going to break this into 2 parts and stop this video.